Or if you guys want to rewatch this video, you guys can rewatch it later. Okay? All right, again, please refrain from side conversations. Let's focus up here. So we're looking at Unit 4. We had different probability rules. Like, these are the basic probability rules. We had the law of large numbers. So I don't know if you guys remember the law of large numbers, but that was like the very first video with Maestas, and he was like, oh, I'm gonna flip a coin and I got heads, and then, oh, I got heads again. Oh, I got heads again. And then he keeps doing that, and it's like, oh, the next one has to be tails. That's actually called the law of averages, not the law of large numbers. Law of averages does not exist for independent events because the previous event does not affect the next one, right? The law of large numbers represents, like, in the long run, you should expect to see the theoretical probability to happen, okay? So we have experimental probability versus theoretical. Experimental is what you get in an actual set of trials. Theoretical is what you would expect it to be. So, like, for example, flipping a coin, you have two outcomes, a heads and a tails. But let's say you flip 10 times the coin. That doesn't mean it's going to be 5 heads and 5 tails, but you should expect it to be about 5 and 5, 50%, okay? In the long run, you will see it equaling the theoretical probability, okay? So let's write that down. Law of large numbers is, like, in the long run, the experimental probability, I'm just going to abbreviate probability, will equal the theoretical probability. Okay, so in the long run, the experimental probability, so like if you take hundreds and thousands of trials, it should equal to like the theoretical, which you would expect to happen. Okay, then probability of event A is probability of A. So how do we calculate the probability of an event? For example, if I take a dice here, what's the probability of me getting an even number? How do we calculate that? How'd you get 50%?
So 6 numbers, 3 even, 3 odd.
3 even, 3 odd, right? So you would take the 3 evens, that's the desired outcome. So it's the number of desired outcomes divided by, you said there's 6 total, right? So you divide by the total number of outcomes.
Bless you.
All right, then probability. I can write this as a fraction, 3 out of 6, or 1/2. So it can be written as fractions, like a 1/2. It could be written as a decimal, like 0.5. And it can also be written as percents. Thank you. I don't know. It took me so long. Percents would be like a 50%. I don't know if I'm recording. Is this thing recording? Recorder is recording. Okay. I took off the webcam thing because I didn't like it. I figured out how to take it off. Okay. And then probability can never be greater than or less than blank. So probability as a decimal, it has to be between 0 and 1. So it cannot be greater than 1 or less than 0. It has to be in between 0 and 1. Usually as a, they say it like that because they look at it as a decimal instead of the percent. We kind of already talked about this one, the law of averages. does not exist for independent events. Sorry, that looks horrible.
No worries.
Averages. So just because like, oh, it's been hot for like the past 3 days, that means tomorrow is gonna be cold. Like that doesn't have anything to do with it, right? But what it means is like, it doesn't matter what's happened before, even if you've had tails for 5 times in a row, that doesn't mean your next flip is gonna be a heads, okay? All right, then the sum of the probabilities has to equal to 1. Like all of the outcomes added together has to add up to 1, okay? Then we have the complement rule. Because they have to add up to 1, then the complement rule is basically getting the probability of not A. That would be 1 minus the probability of A. Because they have to add up to 1, then that means the probability of not getting an A is 1 minus the probability of A, okay? So, for example, if I have a bucket of highlighters here, I have a total of, I don't even know. There's like about 10 in here. Like 10 highlighters in here. And there's only 1 purple. So my probability of purple is 1 out of 10, right? What if I ask you, what's the probability of not getting a purple? You take 1 minus, right? So you get 9 out of 10.
Oh, 1 minus 10.
Well, because it's out of 10, yeah. But it's 1 minus the probability. So 1 minus 1 out of 10 is 9 out of 10. Okay? All right. Then we have events are disjoint or mutually exclusive. If they cannot happen at the same time. So for example, if I roll my die, is it possible for me to get a 2 and an odd number?
Yes.
No.
2 and an odd number in one die is no, because 2 is not odd, right? So it's mutually exclusive. But can I roll a die and I get a 2 and an even number? Yes, that can happen at the same time because 2 is even, okay? All right. So mutually exclusive is they cannot happen at the same time. They have nothing in common, okay? All right, then we had the addition rule and the multiplication rule. So let's look at each of these. The addition rule is the probability of A or B, which is the probability of A plus the probability of B, okay? So this symbol right here means or. Is it like a U, a union? So probability of A union B is probability of A or B is you have to add the 2 probabilities together, okay? For example, what is the probability that we draw a king or a 10 from a deck of cards? So, I don't know if you guys know cards very much. Like, I grew up playing cards, so like, I know the deck of cards very well. There's a total of 52 cards, good. What else do we know?
There's 13.
13 for each suit. So there's 13 like clubs, there's 13 diamonds, 13 hearts. Okay. How many of each card do we have? Like how many kings? 4, right? How many of them are black?
2.
No, like total, I mean. How many total black cards? 26, which means how many of them are red? 26, right? Okay, so that's kind of the basic information that we need. We have,
I got a question.
yeah?
Cards, whenever they talk about that, like, do they include, like, jokers? You know how some cards they have, like, 2 jokers?
Yeah, they don't include, like, if they say a standard deck of 52 cards, then there's no jokers.
Okay.
So we have a total of 52 cards. What's the probability of getting a king? Question?
Yeah, for the, like the AP exam, are we gonna have to know like certain things, like just some basic things about the cards?
Possibly.
Are we able to like ask questions about it, or like?
I have no idea. I don't know. That's a good question, but I don't know. Okay, how many kings are in a deck of cards? 4. 4 total kings, right? Okay, so it's gonna be the probability of kings, and the word or tells us to do what? Add the probability of getting a 10. So the probability of getting a king, you guys said there's 4 kings out of how many cards? 52. Or means add. The probability of getting a 10, how many 10s do we have? 4 out of 52. Yes, there's 4 of each card.
That's all I did.
Okay, so fractions. What do we do with fractions? We only add the what? The numerator. 4 plus 4 is 8. The denominator stays the same. But we need to simplify. 4 goes into both of those, so that's going to be 2/13.
Like that?
Yeah. Multiplication rule. So that's the addition rule. The key word is or means add. Okay? Multiplication rule is the and. So probability of A and B is the probability of A times the probability of B. So this symbol right here is and means you multiply. How can you tell the difference between the two symbols? How do you know if it's or versus and? And has an N, and so it looks like an N.
Oh,
That's how I remember it. I don't know.
get that on the test.
So, what's the probability that we draw a king and a 10? So, probability of king and union is or. Probability of a 10. Okay? The word and means multiply this time. So probably getting a king, that's still 4 out of 52. Probably getting a 10 is still 4 out of 52. But the difference is and tells you to multiply. When you multiply fractions, if you can, I suggest to simplify before you multiply. So 4 out of 52 is 1/13, which will give you 1 over 169. So if you can, simplify the fractions before you multiply. Because if you do 52 times 52, I don't know, but that's a big number. So you might have trouble simplifying after if you multiply first.
And for that, wouldn't it be 4 over 169? Because wouldn't it?
I simplified 4 over 52 is 1 out of 13. Because
Oh, okay. Earlier, hold on, can you scroll up or something? You put it? Okay, wait, never mind.
you got it?
I got mixed up because the 852, the 8 over 52 reduces to 2 over 13, so I put it down as 2/13, like to reduce to, because I went like, yeah. So I got 4 over 169, and I was like, what did I do?
Yeah, okay. And Morgan, you had a question?
For that one,
No. All right, guys, so those were like the basic probability problems. And like the addition and multiplication rule. Let's talk now about Venn diagrams. And I apologize, this is all kind of scattered. There's no flow to it. It's just, I'm just trying to cover everything from Unit 4, okay? So Venn diagrams look like what? The two circles. But what makes it a Venn diagram? They have an overlap in the middle. Good. So if I look at this, it says police report that 78% of drivers stopped on suspicion of drunk driving are given a breath test. Then we have 36% of them get a blood test, and 22% of them get both tests. So what's the probability that a randomly selected driver while intoxicated suspect is given a test, a blood test or a breath test, but not both? And I forget what the part C is, but it's okay. How do you know that we have to do a Venn diagram? There's a key word here that like stands out. Morgan?
I think because it says both.
Both. Good. The both right here, that's the key word. So the key word that tells you need to use a Venn diagram is both. Usually you're going to get like 3 different percentages and one of them will say both. That tells you there's an overlap. So that's your key word to do a Venn diagram, okay? So let's look at our 2 circles here. Our first one is going to be the breath test. And then my second one is going to be the blood test. And then in the middle is going to be the overlap for both of them. And then we also need to have our sample space on the outside. So people that get pulled over that don't get any test at all. They don't get tested at all. They just get, they get a freebie. They just get a warning. I don't know. They don't get tested. All right. So for our Venn diagrams, you want to start in the middle. So my both piece is the 22%. And then the breath test has to add up to 78%. So I can do the like 78 minus the 22. That's going to be 56. And then for the blood test, it has to add up to 36%. So 36 minus the 22, that's going to give us 14%. Okay, and we'll come back to the sample space after, but for now, let's just go ahead and do part 1. Question 1 says, what's the probability that a randomly selected driver while intoxicated suspect gets pulled over and they get tested? Any test. It could be a blood test, it could be a breath test, or they could get tested both ways. What's the probability they get any test done? How'd you get 78? Say what?
It says at the top of 78%, or...
Oh, okay. So this is any test, not just a breath test. That 78 is only for breath tests.
92?
So it's 92. How did you get 92?
I added all of them.
You add all 3 of the individual pieces on the inside of the Venn diagram, okay? So this is a 0.56 plus 0.22 plus 0.14. And that ends up being 92%. There's a 92% chance that you will get tested if you get pulled over if they think you're intoxicated. Okay. All right. And then question number 2 is, what's the probability that you get a blood test or a breath test, but not both? So the both, I'm going to take the breath test, the blood test, but not both. So this is going to be probability of blood or breath, but not both. So that's just the 0.56 plus the 0.14, and I'm not going to add the 22. So what is that? 70?
Yeah.
70%. And there's a part 3, but it still goes with this question. It's just on the other page, the next page. Oh, sorry. The third question, I think it says neither, right? Somebody gets pulled over and they get neither a blood test or a breath test. What is it?
8%.
How'd you guys get 8%?
92 minus 100.
92, good. So you can subtract 1 minus 92%. So neither test would be, this is like the complement rule. So probability of no test is going to be 1 minus the probability of getting tested. We already found out the probability of getting tested was 92%. So this is 1 minus the 92%. That gives you the 8%. So in a Venn diagram, where does that 8% lie? That 8% is on the outside. This is the sample space on the outside here. Yes, Verlis?
Miss, are you ready?
Say what?
Are you ready?
Can you go? Say what?
Track. I gotta charge you.
Didn't you? Isn't the release time at 2:15?
Yeah.
Huh?
Release time is at 2:15, so you can't go yet.
Oh, I think I'm doing it now. I'm gonna show you the track.
Let me see, look. What does it say? Track has a home meet today against Los Banos. Please release track athletes at 2:15.
I know I was gonna get ready.
So you can go at 2:15. Question?
May I use the restroom?
Oh my God, those.
It'll be quick, you know.
You guys gotta chill. Let me finish.
I'll focus quick. I'll shoot off.
Okay. Conditional probabilities. We have a conditional probability now. There's a condition to it. That's why it's called conditional. Okay. And then the condition is going to affect our probability. So conditional I'll do a different color because conditional probabilities, there's a condition, so it affects the denominator. Okay. Usually the key word is like if or given. Sometimes you'll see like who. I'm trying to think of more words, but usually it's like if or given. That's your conditional, okay? So the conditional probability, that's the P, probability of B given A, okay? We read this as the probability of B given A. That's how we read it. Probability of B given A. Okay, so there's a formula for that. That is the probability of B and A happening together divided by the probability of A. So the condition always comes second. Meaning like you're going to divide by the condition, okay? All right, so let's look at an example. Let's say you're going to draw a card at random from a standard deck of 52 cards. So here's our cards again. What do we know about cards again? We have a total of 52 cards. You guys told me there's how many red?
All I know after this work.
It's half of it. There's half of them are red, so 26 is red, which means the other 26 are black. And then we have 13 of each suit. And suit, I mean like 13 hearts, 13 diamonds, 13 clubs, 13 spades. Okay? And then, Megan, what do you know?
There's 4.
There's 4 of each like number or letter. So there's 4 aces, there's 4 twos, there's 4 threes, there's 4 jacks, there's 4 queens, so forth. There's 4th of each. And I think that's the basic information you need to know. Oh, and then face cards. So people always get confused because of the letters, but okay.
I can make a card, right?
Say what? I don't think so. Okay. So you have like, these are the letters in the cards. The other ones are numbers, like 2 through 10. But the letters, what do you notice about like these versus the A? These all have what?
They all have a shape.
They all have like a person, right? They all have faces. They all have faces, so these are all called face cards. The ace is not a face card because it doesn't have a face. Right? Okay. For some reason, people always confuse the aces as face cards because it also has a letter, but face cards have a face. That's why they're called face cards. Ooh. Okay. So for part A, it says, what's the probability that the card is a heart given it's a red card? So there's my key word right there, given. This is going to be my condition. So that's what I'm going to have to divide by, okay? My condition is that I have a red card. So how many total red cards do I have? 26. So I'm going to divide by 26. Out of those 26 cards, how many of them are hearts? How many of each suit?
13.
There's 13. So there's 13 hearts, and all of the hearts are red, so there's 13 out of 26. Okay? So this is actually half of them. Because half the red cards are hearts, the other half are diamonds. Okay? But how do we use the formula? Shh. I'm gonna go over how to use the formula, but I'm not expecting you guys to do it. I'm just gonna show you how to use the formula, okay? Shh. What's the probability of getting a heart given it's red? Well, that's the probability of getting a heart and a red card divided by the probability of having a red card. I need the side conversations to stop, please. Okay, see you tomorrow.
Yes.
Okay. What's the probability of getting a heart and a red card? We just talked about that. What's the hearts and red? Well, all 13 hearts are red cards, so that's 13 out of the 52 cards. Oh my god, those. And then what's the probability? The 13? So what's the probability of getting a heart and a red card? Well, there's 13 hearts and all 13 are red. So it's 13 out of 52 total cards. And then what's the probability of getting a red card? You guys told me there's 26, but there's 52 total. So when you take a fraction divided by a fraction, notice the denominators are the same. So those are going to cancel. Because if you multiply by the reciprocal, The 52 is going to end up in the numerator, so they're going to cancel. So this is just 13 out of 26, which is a half again. Okay? But that is like way super more complicated, so
So is it?
yeah, 50%. But I'm going to leave it as fractions. We're not going to do it like that. I just wanted to show you how the formula works. Okay? Let's look at part B one more time. Part B this time, what's the probability that the card is red given that it's a heart? So what's my condition? It's a heart. So this is my condition. That's what I'm going to divide by. How many hearts do we have? 13. And out of the 13 hearts, how many of them are red? All of them are red, right? So 13 red cards, because they're all hearts, so that's just going to be 1. Okay? All right, I want you guys to try C and D. I'll give you guys like 2 minutes to do C and D. So, what did you guys get for your fraction for part C? Say what? Like the original. What's the 2 over 26? How many of you guys got 4 out of 26? No, why is 4 out of 26 wrong? Because the condition is what? That they have to be red. So you only have 2 red aces. So it has to be 2 out of 26, which is 1 out of 13. Okay? But it's, again, the condition is they have to be red. So that's why it's 2, because 2 of them are red. Okay? And then the last one, what did you guys get for getting a queen given as a face card? 4 out of 12. Because there's 12 face cards, 4 of them are queens. And that simplifies down to 1/3. Good. All right. Let's look now at independent events. How can you determine if 2 things are independent or not? There was a formula, but it's been a while, so let's just go over it. Because I don't expect you guys to remember without having to look at your notes. So if the probability of A and B happening together equals the probability of A times the probability of B separately, then the 2 events are independent, okay? Okay. So, again, if the probability of A and B happening together at the same time equals the probability of A times the probability of B, then the 2 events are independent. So let's look at an example. This one, let's look at the wording. It says 56% of all American workers have a workplace retirement plan. 68% of them have health insurance, and then 49% of them have both benefits. So what's the key word right there that tells us what to do here? Both. Both tells us to do what? Venn diagram. So I want you guys to practice drawing the Venn diagram. The first circle is for retirement. The second one is going to be for health insurance. And then in the middle, you should have both. And then don't forget to do the sample space on the outside, what's left over. Oh my God, that kid is going to drive me crazy. Here you go.
Kids off. Thank you.
Okay, again, you guys are practicing drawing the Venn diagram. All right, double check your Venn diagram. You should have 49 in the middle because that's the both benefits. That's 49%. The retirement has to add up to 56. So 56 minus 49 gives us the 7. And then the health insurance has to add up to 68. So 68 minus 49 gives us the 19. And then if you add those three together, it's 75. So on the outside, you end up with the 25. Okay, so let's look at the first question. Part A says, what's the probability he has neither employer-sponsored health insurance nor a retirement plan? So that's the neither. What is that going to be? The 25, because that's on the outside. Say what? Yeah, I just left the space to draw the picture. I just left the space to draw the picture. But the problems are on the back. Okay. So the neither, that was the 25%, because that's on the outside, right? So that's just 25%. If you have the picture drawn, then that's your work. It's 25%, okay? All right. Then part B, what's the probability he has health insurance if he has a retirement plan? So the emphasis is on if. What does the if mean? What is it? Conditional probability. So what's the probability he has health insurance if he has a retirement plan? So my condition is that they have a retirement plan, okay? This is the condition. So what's the probability of having health insurance given they have a retirement plan? So my formula is the top piece is probability of A and B divided by the probability of A, okay? So what's the probability of health insurance and a retirement plan divided by the probability of the condition, which is the retirement plan? So go back and look at your Venn diagram. What's the probability of having health insurance and a retirement plan? That's the 49% over what's the probability of having a retirement plan? Total retirement plan. That includes the both. 56%. Yeah. So if I plug that into my calculator, I'm going to get 0.49 divided by 0.56. And that gives us, I didn't put the 0.49. So 0.49 divided by 0.56 is gonna, say what? I don't know. I think it does, but you have to like copy it or something. Okay, so if I change that to a percent, that's 87.5%. Okay, then the part C, this is the actual independence part of it. So how do you know if they're independent? If the probability of A and B equals probability of A times probability of B. So we're checking the probability of having health insurance and a retirement plan. If that equals the probability of having a health insurance times the probability of having a retirement plan. So the first piece, what's the probability of having health insurance and a retirement plan again? 49, because that's the overlap. Does that equal probability of health insurance? Total health insurance is what? Health insurance, I think, was 68. The retirement plan is a 56. If I multiply those two together, 0.68, oops, 65, 68 times 0.56 equals, that's 0.3808. I can't minimize it. So 0.3808, are those equal? Nope. So then these are not independent. Okay, our next thing, so far that was all just review. We had already done all that. Venn diagrams, conditional, we did independence, we did basic probability. We did not do tree diagrams though. We're probably not going to finish, but let's just see how far we can go. Using tree diagrams here is when you have to actually draw a picture. So this is an example where it says a private college report contains these statistics. So we have 70% of the incoming freshmen attended public schools. So I can draw a branch, that's my first branch, is they attended public schools. So that was a 70%. Which means the rest came from other schools. So the other could be private schools, it could be charter schools, it could be being homeschooled. We don't know exactly, they didn't break it up into categories, it's just the other. It has to be what? Has to add up to 1, so that's going to be 0.30. Okay. My next statement says 75% of the public school students who enroll as freshmen eventually graduate. So that's my second branch because it talked about one of the first branches. It talked about the public, which is my first branch. So it branches it off of the public because it mentioned public again. Okay? So it says they eventually graduate is 75%.
Miss Big, we all put it on the side of our paper.
It's all good. We can put it on the other side.
What?
Because you have it drawn on the paper, right? And now you're drawing outside of the paper, so we could all draw it on the edge of our
Oh. My bad. Sorry. I should have. You can just like draw it to the side like this then. Try like that. Sorry, I should have given you a heads up. My bad.
That's why you don't use pens.
I know, mija. That's why you use pencil.
Pencil. See this missing? Pencil.
Oh my God, those. Okay, so if 75% graduated, what does that mean about the rest of them? They didn't graduate. So no graduates. It's gonna be how much? What percent is that? 25%. Okay. And my My last piece of information is 90% of the other freshmen eventually graduate. So again, it's talking about the other branch, so it branches off of the other. So the other is 90% eventually graduate, which means how many of them do not graduate? 10%. So what do you guys notice? Is there any evidence that a freshman's chances to graduate is going to depend, upon what kind of high school the student attended? Do you think that's enough evidence? Like public students graduate only 75% versus like the other students graduate 90%. Do you guys think that's enough evidence?
Yeah.
Yes. So we're just gonna stop there. We're gonna say yes because like 75% of public graduates and 90% of other graduate. Okay, so we'll finish this off tomorrow. You guys can clear your desk, grab the spray, and then wipe down the desk for me, please.
Like that.